Have you ever looked up at the night sky and felt that, like, just that awe,
Mhm.
wondering about the stars and how we even know, like, what they're made of?
Yeah.
Well, get ready because today's deep dive, it's going to equip you with some serious knowledge,
Yeah.
okay? We're talking about the force that, like,
Yeah.
connects us to the cosmos, right? Electromagnetic radiation.
hmm
We're diving into excerpts from Feynman's lectures on physics.
Oh, yeah.
And trust me, having an expert guide through these, well, they're brilliant, but they're dense.
Dense is right.
They're dense texts. It's a lifesaver.
Oh, absolutely. You're not wrong about the density, but the insights we can gain from them are pretty mind-blowing. One of the things Feynman really emphasizes is how physics is just full of these aha moments, where things that seem totally different turn out to be like interconnected.
Okay, I love a good aha moment.
Right.
So what's one that comes to mind, like when we're talking about something as fundamental as electromagnetic radiation?
Well, think back to the 1800s. Scientists, they're studying electricity, they're studying magnetism, but they thought these were completely separate forces, right?
Mm-hmm.
Then along comes James Clerk Maxwell, and his work is like the ultimate plot twist.
Ooh, I'm intrigued. Lay it on me. What did Maxwell figure out?
Maxwell's equations, and I'll spare you the mathematical details for now.
Please, yes.
But they basically said, hold on, electricity, magnetism, not separate at all. They're two sides of the same coin. He called it electromagnetism.
Okay, I'm seeing a tiny bit of light at the end of this tunnel.
Right.
No pun intended.
Yeah.
But how does light tie into all of this?
That's the really revolutionary part. Maxwell's equations didn't just unify these two forces. They predicted that light itself was an electromagnetic wave. Before this, the nature of light, it was a total mystery.
Whoa. Okay, so that light from my desk lamp, the sun, those distant stars, it's all just electromagnetic waves.
It's true.
My mind is kind of blown right now.
Yeah. And these waves, they behave in fascinating ways, right? Now, you might know that forces like gravity, they follow the inverse square law, right?
Mm-hmm.
Meaning get twice as far away and the force is 4 times weaker.
Right.
Electromagnetism has that component, but it also has a part that doesn't weaken as rapidly over distance.
Hold on. I'm picturing myself trying to outrun gravity.
Oh, it's great.
And successfully, I might add.
Right.
But you're saying electromagnetism has a trick up its sleeve.
Exactly.
It's less weak at a distance.
That's why we can communicate with spacecraft billions of miles away via radio waves. Why we can see light from stars across unimaginable distances. This unique property allows electromagnetic waves to travel so far.
That is seriously wild. Right. So we've established this is all very important, but how does it actually work? When I picture a wave, I think of water, but obviously that's not what's going on with light.
Right.
I know.
It's a great question. It all comes down to electric fields and what happens when charges move. Now, Feynman, he does provide a pretty intense equation.
Of course.
No need to pull out your calculators, I promise. But the key thing that it shows is this. When a charged particle accelerates, it creates this disturbance in the electric field around it.
Okay, I'm trying to visualize this.
Sure.
So imagine like dropping a pebble in a still pond.
Yeah.
That creates ripples that spread outwards, right? There's something like
That's
that?
a helpful analogy, yeah. Instead of ripples on water, picture disturbances in the electric field, right? And get this. These disturbances, they don't just travel outward, they travel at the speed of light.
The speed of light. Okay, this just keeps getting more and more amazing. But why acceleration? Why not just movement?
Great question. So a charge moving at a constant speed does create a field, but it's constant. It's the acceleration, the speeding up, the slowing down, or changing direction that causes this field to fluctuate. And it's those fluctuations that we perceive as electromagnetic radiation.
So more acceleration equals like stronger fluctuations, stronger radiation. Like if I could shake a flashlight back and forth really, really fast,
Yeah, you got
it would get brighter.
More acceleration means more energy is being pumped into those disturbances in the field, right? Resulting in more intense radiation.
This is incredible, but how do we actually know any of this is true? It's not like we can see these fields like rippling outwards, or can we?
You're right. Directly observing these fields is tricky, but we can see their effects. Feynman uses this really cool analogy of a painter, capturing a fast-moving scene.
A paint? Okay, color me intrigued. How does a painter help us understand, like, invisible fields?
Well, imagine the painter's trying to capture this horse race. Right at the finish line. The light bouncing off those horses, the ones that allow the painter to even see them. It takes time to travel to the canvas.
So what the painter's capturing isn't, like, the present moment, but things as they were a tiny fraction of a second ago.
Exactly. It's a subtle delay, but a real one. And it's similar to how we study electromagnetic waves. We can't see those changing fields instantly. We're always observing the past based on how long it takes the signal to reach us.
Okay, I'm starting to see the connection. But we're not just, passively observing light from horses here. How did scientists actually test these ideas about electromagnetic waves?
This is where it gets really cool. Feynman, he describes this experiment using incredibly simple tools, two wires sticking up like those antennae on a vintage radio. We use a signal generator to make charges oscillate up and down these wires. Picture a microscopic game of ping pong, but with electrons.
Okay, I can visualize that.
Yeah.
But how does this, simple setup prove anything about waves traveling at the speed of light?
Here's the ingenious part. We use a second set of wires, identical to the first, as our detector. It's like sending a message through thin air. But our message is carried by these fluctuating electric fields.
Wait, so we're creating electromagnetic waves with one set of wires
Yeah.
and then picking them up with another. That's wild.
Right.
It's like those string phones we used to make as kids, only a million times cooler.
Exactly. And by carefully positioning these wires, we can actually prove some of the things our equations predicted. For example, we can demonstrate that the electric field is perpendicular to the direction the wave travels.
Okay, now you're just showing off. Walk me through that one.
Okay, so picture our two-wire setups, right?
Mm-hmm.
When the detector wires are parallel to the generator wires, we get a strong signal, meaning the electric field is vibrating in the same direction. But here's the mind-blowing part. Rotate those detector wires 90 degrees so they're perpendicular and silenced.
No signal at all.
Yeah.
So the electric field must not be vibrating in that direction. We're literally using these wires to map out something invisible.
Isn't it incredible? And it gets even better. Remember how we said charges need to accelerate to create those fluctuating fields? Well, we can actually control whether the charges in our two-wire setups are moving in sync or not.
Refresh my memory. What's the technical term for in sync again?
We call that being in phase. Imagine two dancers moving in perfect unison. When our charges are oscillating in phase, it's like they're doing the same dance move at the same time.
Got it. So what happens when they're out of phase, like those dancers just tripped over each other's feet?
That's where it gets really wild. When those charges are oscillating 180 degrees out of phase one set going up, while the other goes down, the signals cancel each other out.
Whoa, they disappear.
In a way, yes. Their effects are negated because the electric fields they create are now opposing each other. It's like adding one in a meadow, you're left with zero.
My mind is officially blown. So by messing with the timing of these oscillations, we can make electromagnetic waves appear and disappear at will.
Exactly. And this is not just a cool trick. This principle of wave interference is the foundation for countless technologies we use every day. Ever use noise-canceling headphones?
All the time. It's how I survive noisy commutes and open office plants.
Well, those headphones are using this exact principle, generating sound waves that are out of phase with the noise you want to block, effectively canceling it out.
So next time I'm enjoying some peace and quiet, I'll be thanking those out-of-phase waves. But hold on, I thought we were talking about light, radio waves, the kind of stuff that travels through space. This all seems very sound-related.
It's a great observation, and it highlights just how universal these principles are. Sound waves, water waves, electromagnetic waves, they all share this property of interference.
So it's the same basic principle at work, just with different types of waves.
You got it. When we talk about sound canceling, we're dealing with pressure waves in the air, interfering with each other. With electromagnetic radiation, those waves are fluctuations in the electric and magnetic fields, zipping through space at the speed of light.
And speaking of space...
That's the part my brain keeps, getting stuck on, right? Sound needs air, water needs, water. But light can travel through the vast emptiness of space. How's that even possible? It's one of the most mind-boggling things about electromagnetism. Those fluctuating fields we've been talking about, they don't need any kind of medium to travel through. They can zip through the vacuum of space at, the ultimate speed limit.
So that starlight we talked about earlier, it's been traveling for millions of years through pure emptiness, all because of these self-propagating disturbances in the electromagnetic field. That's just, whoa.
It really is amazing. And remember that look-back time we discussed, thanks to the speed of light? Well, that comes into play even with our two-wire experiment.
Really? I thought that was more of a, cosmic scale thing. Tell me more.
Well, think about what happens as we move our detector further away from those oscillating wires, right? We have to adjust the timing more and more precisely to maintain those interference patterns, those zones of cancellation or reinforcement.
So those patterns are literally showing us the delay caused by the fact that even light takes some time to travel. It's like we can see the speed of light in action.
You got it. And it gets even more interesting when we think about having two sources of electromagnetic waves, like our two wires, and how their signals interact with each other.
Okay, my mind is primed for like more mind-blowingness. What happens when you have multiple sources? Does it just get like twice as bright or something?
It's so much cooler than that. Think back to those ripples on a pond. If you drop two pebbles in at the same time, their ripples will interfere with each other, creating these beautiful patterns of peaks and troughs. The same thing happens with electromagnetic waves.
So you get these zones where the waves either amplify each other or cancel each other out, creating like bright spots and dark spots.
Exactly. It's like a cosmic dance of waves, and the patterns they create can be incredibly complex, beautiful even. And guess what? This principle of wave interference, it's what allows us to see.
Wait, what? How does that work? I thought we saw it because light bounced off objects and entered our eyes.
You're right. But it's the wave nature of light that determines how it bounces, how it bends, and ultimately how our eyes perceive different colors. It all comes down to the wavelength of those electromagnetic waves, the distance between those peaks and troughs we were talking about.
Okay, now I'm seeing the world in a whole new light. No pun intended. So different wavelengths mean different colors.
Exactly. The visible light we see is just a tiny sliver of the entire electromagnetic spectrum. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, they're all forms of electromagnetic radiation, just with different wavelengths, different energies.
It's mind-blowing to think that something as seemingly simple as like the distance between those peaks and troughs in the electromagnetic field can determine such a vast range of phenomena.
Isn't it incredible? And honestly, we've only just scratched the surface of what there is to learn about this fundamental force of nature.
Well, you've definitely given me a whole new appreciation for the invisible forces that like shape our universe. I'll never look at my phone, my microwave, or even a sunset the same way again.
That's what we love to hear. Keep asking questions, keep exploring, and remember, the universe is full of wonders just waiting to be discovered.